Okay, so the first thing you're going to want to do is look at your data, and you'll want to put it into some sort of format, kind of like I've got on the screen, where we've got the cells from A1 through A8, B1 through B8, C1 to C8, keeping in mind what each of these are. So A1 to A8 is simply just looking at hydrolysis of substrate. B1 through B8 and C1 through C8, these are looking at substrate only. Down here for D1 and E1 through D8 and E8, that's your first inhibitor. And then down here we have the second inhibitor. So group everything together according to how you're going to use it, because we need to basically combine what we need together. So the other thing that kind of makes this easier is you'll notice that some of these cells, like right there, we've got a value of 0.2. Easy way to fix all this is just go in here, select all these cells, and go to Format and go to Cells. And we're just going to set the number to have 3 decimal places. And what that'll do is all of a sudden that one now has 0.200 on it, so it just looks better, in my opinion. So, and it makes it a little bit more consistent and kind of easy to deal with. So I'm going to do the same thing down here, and then same thing down here as well. So that way everything has 3 decimal places. So now we want to look at the absorbance. We want to look for any absorbance change in the absence of enzyme. So if you'll, basically the easiest way to do this is to say this equals this cell minus this cell. And you notice it's 0.001. And then if we just drag this down for several cells and get rid of that last one, we notice that it pretty much just, the fluctuation is so minimal, we can actually say equals average of these right here, and essentially it's 0. So we can then basically take this, drag it all the way out there, and drag that average out. And we notice that basically there's essentially no change. The change is so small as to be infinitesimal in this case. Now, if there is a change, you're going to have to factor that into your data. You're going to have to subtract that particular substrate concentration, the spontaneous hydrolysis from that particular substrate concentration. The only place you might see any significant change would be out here in columns maybe 6, 7, and 8, because there you're dealing with a high concentration of substrate. And with that, more likelihood that you're going to have spontaneous hydrolysis of substrate since you have so much substrate around. So now we're essentially going to do the same thing we just did here on all these other rows. So I'm just going to copy this and I'm going to paste it right there. And this is telling us, once again, B1 is simply looking at hydrolysis of substrate or any sort of activity with no substrate present. So which we expect that the absorbance there should be pretty much nothing, no change in absorbance. And then we're increasing substrate as we go across. And then we're going to copy this and paste that there. And we're going to do the same thing there. The key thing is we want to actually look at the actual changes. And for instance, you'll notice here that we go from 0.35, 0.39, 0.3, and all of a sudden we drop to like 0.017, 0.016. So we've definitely had a significant decrease in the activity as we get to the kind of the further on in the time process here. And in this case, I did this data with 1 minute time points. So when we get out here to 4 and 5 minutes, we're seeing that we're pretty much running out of substrate in that case. I'm actually going to want to delete these 2 points because they're not really in line with the rest of the data we see. We come over here and we set that last point is really out of line, so I'm going to get rid of that. Here we have kind of a weird situation, and this is one of those cases where if you look at the average of this, it kind of looks like it did towards the end of the run. So it's more likely that this initial data point, we had some poor mixing going on. So I'm going to have to actually keep all of those. Here, it's pretty indicative of the entire set. Same thing here, although we're not seeing much of an increase. Basically, we're looking at a point here where we're probably getting to enzyme saturation. So I'm going to just copy this, and I'm going to paste it over here. And we see somewhat similar results. I can pull this down to see if we get better data there. We don't really, so I'm just going to go ahead and delete those again. Do the same here. And with that, we'll go ahead and just keep that data point. Same thing with the rest. So basically, the activity that we see in row B should be almost identical to what we see in row C. And if we look at the change in absorbance, we're seeing a relatively similar. If we compare, for example, B2 with C2, there's a drop there, but in the next one, here versus here, pretty similar. This one is identical, so a little bit of a difference there. That's basically what you're looking for. So you want to actually compare those points. So now I'm going to copy this entire block, and then I'm going to go down here, put that in that cell right there, and I'm going to go ahead and paste that. Do a similar thing here. Once again, we're just looking at now the inhibitor study, and we see that we'll go ahead and extend that down to see. This is once again most likely a poor mixing, but I'm going to go ahead and keep all the data there because it looks a little bit more indicative. If we look at this, I'm going to extend that down. I'm going to go ahead and keep all that data as well. So do the same thing over here. Probably best to keep that because we did have that 0 point there, a little bit weird. And then I'm going to go ahead and keep that as well. So basically, if we look at these values, so for example here, 0.027, 0.028, compare that up here to 0.053 and 0.053, we definitely see a decrease in our activity, which is what we expect with an inhibitor. So at this point, I'm going to do the same thing down here, paste those here and here, and once again go down and take a look. These differences all look pretty much what we expect. Generally, we're seeing an increase across there, a little bit more activity over here at the higher substrate concentrations, but in general, this is going to be a fairly usable data set. So that's what you're going to want to do to just assess whether or not the data set is looking good. So. Okay, so at this point, we're now going to average these values together. So I'm going to basically say equals this plus this divided by 2. And then I will drag that across here to get the average values for each of these. And then I'm going to copy that. And I don't have any space. Hold on. We need to go down here and make a little bit more space. Okay. So now if I could just copy this and put it down there, and then we'll do the same down here. Now I've got the averages for the two different data sets. So now the one other thing I want to do is basically make this only 3 decimal places. So, and this one's probably fine, but I'll do it at there as well. And okay, so so now we've got the averages for our data set. So we've got the average increase in absorbance, and this is going to be in absorbance per minute. So now we want to convert that into absorbance or product versus time. And I'm going to actually have to move this down a little bit to give myself a little bit more space here. Okay, so we can convert absorbance, delta absorbance over delta time by basically just converting absorbance into product. Delta absorbance per time to delta product versus time, basically by using Beer's law. So we've got absorbance equals extinction coefficient times concentration times path length. So we want to basically solve for concentration. So we want concentration equals extinction coefficient times path length divided by absorbance. So so we're going to, in order to do that, we will take our, we're going to say this equals our absorbance divided by the extinction coefficient, which is 15,000 molar to the minus 1 centimeter to the minus 1. And then in terms of our path length, we know that the path length in a microplate is 0.28 centimeters per 100 microliters. We've got a volume of 200 microliters, so we've got to take that 0.28 and multiply it by 2.5. So we end up with 0.7 for a path length. So we divided by our extinction coefficient, and then now we need to divide again by 0.7 for 0.7 centimeters, and that should convert this into a concentration. So, and the concentration in this case is going to be molar. I figure the easiest thing to do is to use micromolar. You're welcome to use nanomolar, millimolar, whatever you want. But I'm going to, since this is in molar and I want to change this to micromolar, I'm going to say that equals the value we just obtained. I'm going to multiply that by 1e to the 6th. So that actually gives me a nice whole number there. And I'm going to, once again, format this so that we only have 3 decimal places so that the cells don't get ridiculously big here. So I'm going to drag that all the way across. And you'll notice that, yes, it says 0.000 here, but it's in scientific notation. Once you multiply it by a million, it looks fine. Although that one looks weird. And I actually see what I did. I need to fix this. I've got this cell should be this one, not the one next to it. So we'll fix that, drag this across, and that should fix all our values. Okay, so now it's increasing with increasing substrate concentration. Okay, so I'm going to take these cells here, and I'm going to paste them down here, and I would do the same thing down here. So now in each case, we have converted this into the amount of the product per minute. So we've got essentially a velocity there, which is what we want. And now we just need to basically make a substrate versus velocity, a table for substrate and velocities. So in terms of substrate concentration, so I'm just going to have these correspond to the columns that were on our plate. So and this will be the substrate concentration, and this is going to be in micromolar. So we've got 0, 50, 100, 200, 400, 600, 800, and 1,000 micromolar. And then our velocity, and I'm just going to put no inhibitor here, and velocity inhibitor 1, and velocity inhibitor 2. So the easiest way to do this is just basically we want to put this cell right here, the contents of this cell, in that box. So I'm just going to say equals this. Return equals this. Return equals this. Return equals this. And so on. And there are other ways to do this, but this is the quick and most easily explained way of doing this. Then I'm going to, the beauty of this is that you can then drag this down here. And we can say equals this. And then we'll do the same thing here. Oops. So now that we've got the substrate versus the substrate concentration and velocity, we can actually make our plots. So, and I'll just really quickly show you how to do a Michaelis-Menten plot. So I'm going to select my data. I'm going to go up here to Insert and go to Chart. I'm going to do an XY scatter. And basically, it's going to have something that looks like this. So we've got velocity versus substrate concentration. We can add a line to this. Basically, we can, for this, we would want to actually change the type of chart, and we're going to change it to that. So, and that gives us fairly close. We can actually probably get to look a little bit better. No. The alternative is you can just leave the points there, and if you want to hand sketch it, I'm not going to go into how to fit a curve to this. So, but the main thing is just get a straight velocity versus substrate plot from that to look somewhat decent. So the main thing is we want to take these values and we want to convert this into the data that we need for a Lineweaver-Burk plot. So we're going to go 1 over the substrate. Here, I'm going to actually move this down one line. So this is going to be 1 over substrate, 1 over velocity, etc. So this is going to equal 1 divided by, we can't do it for this one, sorry. We're going to say equals 1 divided by this. And then fill in all those. So now we've got our reciprocal data. So now select this, insert chart. We'll go to XY scatter. And we've got a line there. So I'm going to get rid of these grid lines. Excel really likes grid lines for some reason. And then we're going to add a trend line. And we want to make sure it's linear. And we want to display equation on chart. We also want to display R squared. You can change what the line looks like by going to the fill, and usually we want a solid line, so it's going to look something like that. You can move this down out of the way in this case. You can change the color of your line as well if you want. Now the next thing we want to do is we're going to add data to this. So we're going to select the data that we're going to add, and we're going to, actually the easiest way to do this is chart add data, and the range that we're going to add is going to be this right there, and we'll hit OK. And now there's our second set. So now we'll click on that. And we're going to add another trend line. And once again, change this to a solid line. And then we want to display equation on chart and display R squared value. So, and we can, like I said, you can move these around fairly easily. And then now we're going to add one more set of data. So chart, add data. And now we're going to select that column and we'll hit OK. And it ends up down here. And I will once again say add trend line. And we're going to display equation and display R squared. So this is why I move these around so that we remember what equation belongs to what which line. And then I'm going to go to the line and we'll change the line to a solid line. So now we've got our down here, and you can make this bigger so that you can look at it. So here's the equation for the line with no inhibitor present. Equation for the line with the inhibitor, with our second inhibitor, and then with our first inhibitor. So, and then using those equations, you should be able to calculate Km and V max based upon the Lineweaver-Burk equation of 1 over velocity equals Km equals 1 over substrate times Km over V max plus 1 over V max. So, and basically for that, you're going to use the y-intercept to calculate your V max, and then you know the slope equals Km over V max, or Km equals slope times V max. So Make sure that you keep your units consistent. So since I had substrate concentration in micromolar, so thus I'm going to have my Km is going to be in micromolar. My velocity, because I converted into micromolar per minute, my velocity will be in micromolar per minute. So you want to make sure that your report in those use being consistent with your units.